Imagine you're standing in the rain, holding nothing but a window frame. If you tilt it flat, the maximum amount of rain pours right through it. But if you turn it sideways so it's just an edge to the rain, well, zero rain gets through. That amount of rain you're catching, that, right there, is magnetic flux. And today, we're going to build the entire foundation for all of electromagnetic induction on that one simple idea.
So let's really dive into this because it's a simple but incredibly powerful idea. This whole rain window analogy is going to make the pretty abstract concept of magnetic flux super easy to picture in your head. And trust me, it's the key to understanding everything that's coming up next.
All right, so let's break this analogy down piece by piece. We're going to connect every part of this picture, the falling rain, the size of your window, even the way you're holding it, directly to the physics of magnetic fields.
Okay, so what is it officially? Well, magnetic flux, which we represent with the Greek letter phi, is just the measure of the total magnetic field lines that are passing through a specific area. But let's be real, it's way easier to just think of it as the total amount of rain your window frame is catching. The more rain you catch, the more flux you've got. Simple as that. Now let's see how this awesome analogy builds into a really elegant and simple formula. And don't worry, every single part of this equation relates directly back to our little rainstorm.
And here it is, phi equals b times a times the cosine of theta. This is it. This is the one formula you absolutely have to know for magnetic flux. So the big question is, what do these letters actually mean in our rain and window story?
Well, B is the magnetic field strength. Think of that as how hard it's raining. Is it a light drizzle or a total downpour? A is the area of your loop, which is just the size of your window. Obviously, a bigger window is going to catch more rain. And finally, theta, that's the angle which represents the tilt of your window.
But that angle, theta, this is a really crucial detail. It's a classic trap that a lot of people fall into, so let's get super clear on exactly what it represents.
Okay, let's settle this right now. Theta is not the angle between the rain and the flat surface of the window. No way. It is always the angle between the rain and the normal. That's just an imaginary line that's sticking straight out, totally perpendicular to the window's surface. You have to always use the angle to the normal. So here's the bottom line. You get the absolute maximum flux when your window is perfectly flat, facing the rain head-on. In that position, the normal line is pointing in the exact same direction as the rain, which makes the angle between them, theta, 0 degrees. And since the cosine of 0 is just 1, the flux is simply b times a. Maximum rain catch.
So why are we so obsessed with the amount of rain we're catching? I mean, who cares? Well, here's the big secret. In electromagnetism, it's not the flux itself that's interesting, it's changing the flux. That's what generates electricity. And it turns out there are exactly 3 ways you can change how much rain your window catches. So, here are the 3 levers you can pull. 1, you can change B, the magnetic field strength. That's like making the rain heavier or lighter, maybe by moving a magnet closer to a coil. 2, you can change A, the area. You can just make your window bigger or smaller. Or 3, you can change theta, the angle, by tilting or spinning your window in the rain. Do any of those 3 things, and you are changing the flux.
Okay, theory is awesome, but let's get our hands dirty and see how this all plays out in the real world. We are going to tackle a typical problem you might find on an exam, something based on a 2025 CBSE board pattern question. So the setup is this. We've got a circular coil, and the magnetic field it's sitting in is changing. First, the field drops all the way to 0 over a certain amount of time, and then it ramps back up to its original strength, but over a different, longer period of time. Here's all the data laid out for us. In case 1, the field goes from 30 millitesla down to 0 in just 20 milliseconds. That creates a voltage, or an EMF, that we'll call E1. In case 2, the field goes from 0 back up to 30 millitesla, but this time it takes 40 milliseconds, creating an EMF we'll call E2. Our job? Find the ratio of E1 to E2.
Whoa, stop right there. Before you touch a single number, this is a massive trap alert. You absolutely must convert everything to standard SI units first. Milliseconds have to become seconds, and milliteslas have to become teslas. This is such a common way to lose points, so please don't fall for it.
So, let's just do it. 30 millitesla becomes 0.03 Tesla. 20 milliseconds is 0.02 seconds, and 40 milliseconds is 0.04 seconds. Okay, now that our units are all playing nice, we can actually solve this thing. Okay, Let's walk through the logic here. First, and this is the key, you have to recognize that the total amount of flux change is exactly the same in both cases. The field changes by 30 millitesla each time. Second, remember that EMF isn't about the amount of change, it's about the rate of change, how fast it happens. So when we set up the ratio of E1 over E2, that flux change term, delta phi, is on the top and the bottom, so it just cancels out. And that leaves us with a super simple ratio of the time intervals.
And just like that, the calculation becomes incredibly easy. The ratio E1 over E2 is just the second time interval divided by the first. That's 40 milliseconds divided by 20 milliseconds, which gives us 2. The first EMF is double the second. Why? Because the change happened twice as fast.
And that right there is the core takeaway from this whole problem. If you remember nothing else, remember this little phrase. A faster change in magnetic flux gives you a bigger induced voltage. It's that direct. So we have totally mastered flux. We know what it is, we know how to calculate it, and we know the 3 ways to change it. So now let's connect all this to the bigger picture. How does changing flux actually create the electricity that powers pretty much everything in our world?
That connection is wrapped up beautifully in one of the most important equations in all of physics, Faraday's law of induction. This is the mathematical link we've been building towards. It says that the induced EMF, that's the voltage, epsilon, is equal to the rate of change of magnetic flux. Hey, we just proved that, didn't we? The faster the flux changed, the bigger the EMF. This little equation is how we make the world run. But hang on a second. What about that minus sign? Why is it there? Well, that little negative sign represents something called Lenz's law, and it's all about nature's stubborn tendency to oppose any change. It's a really cool and kind of weird concept, and it is exactly what we're going to tackle in our next explainer.